Hello there to everyone remote learning in quarantine land. So I'm going to do another example of the altitude on the hypotenuse theorem because I have received a lot of these questions and I got another one today. I would suggest watching the entire lesson. I did a video on altitude on a hypotenuse theorem a day ago or so. Watch that one if this one goes too quickly for you, because I'm really just going to briefly go over what we talked about and then get into solving this one. So when you're given these problems, you are looking at a right triangle that has an altitude that is dropped down to the actual hypotenuse of that triangle. So that's what creates this special relationship. We've seen altitudes in triangles before, but what we're looking at is a right triangle with an altitude dropped to the hypotenuse of that right triangle, and it creates three similar right triangles. So if you remember what we should know about altitudes, they are perpendicular. Perpendicular means they create right angles. So your diagrams are going to look like this, or a rotation of this figure. It won't always be facing this way. So let's just break up these three triangles and show you what I'm talking about. If we start with the largest triangle ABC, we go from A to B to C to D. Now what I want to do is just rotate it up and kind of reflect it so that all of the right angles are going to be at the bottom left so we can see these more clearly. So there we have the largest triangle. Next, going to the medium triangle, ADC, we go from A to D to C. We are going to just, again, rotate it up and bring it down so that the right angle is pointing bottom left. And the smallest triangle is already facing the right way. It's really easy to see. We have triangle CDB, and we could just bring that down again, D being the right angle, and it's pointing left. In the last video, we talked about how we knew we had congruent angles. We called angle A X, we called angle B Y, and then we found how ACD is equal to Y and BCD is equal to X. So I'm going to go ahead and pop those in there so you know what we're looking at. Now we can see that we have three clear similar right triangles. Remember, similar triangles, all you need is two congruent angles, because if you have two congruent angles, then you have three, because all three have to add up to 180. So if you've got two that are congruent, you definitely have three. All right, so let's summarize what we talked about. This is going to seem really fast, but again, this is just a summary of what we learned. All right, the altitude on the hypotenuse theorem is just a bunch of proportions that deal with the three triangles within this figure. So you have to ask yourself, am I looking at the large to the small, the large to the medium? What two triangles am I looking at? So if you're looking at the large triangle to the small triangle, you're going to start by comparing the large hypotenuse to the small hypotenuse. And what happens here is this small hypotenuse, while it's the hypotenuse in the small triangle, it also serves as a leg in the larger triangle. And that's the relationship that's going to keep coming up over and over. So if I compare AB, the hypotenuse of the largest triangle, to the AC, hypotenuse of the smallest triangle, the AC, the hypotenuse of the smaller triangle, does double duty. It is also the smallest leg of the large triangle. So that's what we're going to compare. Large hypotenuse to small hypotenuse. And when I say large hypotenuse, I mean large triangle. So large triangle hypotenuse to small triangle hypotenuse. That small triangle hypotenuse becomes the smaller leg to the larger triangle. So we're going to just pick the corresponding leg, which would be the smaller leg to the small triangle, because we're only looking at large to small triangles. Putting letters with this ratio, let's look at it. It's AB, large hypotenuse, to AC, small hypotenuse. AC becomes the small leg for the large triangle, so AC to AD. Now there's a special relationship we talk about where AC is the geometric mean. You don't need to remember that to solve these. All you have to know is how to solve a proportion. And you do that by cross-multiplying and making your equation. So when we cross-multiply, we get AC squared is equal to AB times AD. And this is the equation you'll use to solve for side lengths. So AC becomes what we call the geometric mean of sides AB and AD. And all that means is if you square AC, it is equal to the product of the sides it's the geometric mean of. So AC squared is equal to AB times AD. That's all that means. Now, if you're looking at the large to the medium triangle, we're again going to compare hypotenuse. So the large triangle hypotenuse to the medium triangle hypotenuse, and then that medium triangle hypotenuse will be doing double duty. So AB to CB this time, because CB is the medium triangle's hypotenuse. And if we look at it, yes, CB is the hypotenuse of the medium triangle. It's also the longer leg of the large. So we're going to say longer leg, and we need the longer leg then of the medium. So it will look like AB to CB is equal to CB to DB. Cross multiply, you get CB being the geometric mean between the sides AB and DB. All right, last relationship is really easy to see. You're just looking at the small and medium triangles, and you don't have to look at a hypotenuse. You're literally comparing these like we would any other similar triangles. We're going to say small leg to large leg, and then that small leg CD, or that large leg CD of the small triangle, is the smaller leg here. So small leg to large leg, small leg to large leg. Cool part is CD is the altitude. So it's really AD, small leg to large leg. This large leg is the small leg of the medium to the other large leg, right? Large leg of medium. So we'll put it into proportion form. AD to CD is equal to CD to DB. CD then becomes the geometric mean of AD and DB. Basically, the altitude squared is equal to the product of the segments of the largest hypotenuse. That's the relationship you want to get there. All right, now let's get to the problem that we were given. So we were given this problem, and it says find the exact value of z. Exact value usually means you're dealing with a square root, but I think in this case it doesn't want you to round the decimal we're going to get because you're probably putting it into a computer system. So the first question you ask yourself anytime you do these, what two triangles are we working with? We are working with the large triangle and the small triangle. How do I know? Well, we were given z, the large hypotenuse, and we were given 27, the smaller side of the larger triangle. So that's definitely the large triangle. Then we were given 16, the smaller side of the small triangle, and 27, the hypotenuse of the small triangle. So we are definitely working with the large and the small triangle. Let's go ahead and pop vertices in. I know that they're not given, but we can just pop them in because we just learned the rule and it might help us. So we're going to use our very first relationship. AB, large hypotenuse to small hypotenuse, is equal to small hypotenuse to the smaller leg of the large. So we're going to get z is to 27, right? Large hypotenuse to small hypotenuse. As that small hypotenuse becomes a leg, so as 27 is to 16, the smaller leg of the small triangle. Now this isn't going to be as pretty as some of our other examples, but that's okay. We're going to cross multiply. We get 27 squared equals 16 times z. 27 squared is 729 equals 16z. We're going to divide both sides by 16 because we have to get z by itself. So divide both sides by 16. We get x equals 45.5625. You need to keep all of that because it said find the exact value. Don't round this answer. All right, I hope that helped. If you have more questions, you know where to find me. My email's on my YouTube. Search my YouTube. I have tons of videos up there. Maybe your question has already been asked by someone else. Till next time, take it easy.